Well, folks, thanks for coming to this very special Phosphorus Live. I'm John Terrill, the CISO here, and with me is Chris Rouland, our founder and CEO. And we want to talk to you today about exploiting the kind of OT and ICS world. And we're planning to do that by taking a look at industrial and manufacturing examples and kind of digging into making this problem real. When I look at this stuff, I see a lot of really talented vulnerability researchers that write exploits, and a lot of that's for the controllers or the PLCs themselves. And they do really fascinating work, but most people don't have the actual devices that these things control. So it's tough to see what the actual impact is. So we wanted to walk through some of that. But I'm going to let Chris give us an intro and just kind of level set, and then we're going to dig into hopefully what's going to be some fun.
All right. Well, thanks, John. Thanks for teeing that up, and I'm glad to be here with you. We've been doing this together for a while. John and I go back to the X-Force early days, and it's fun to still be able to break into computers with someone. And so, we're using this term extended Internet of Things. It's one some of the industries use. I think Clarity, CrowdStrike also use it. We need some kind of term to refer basically to embedded devices. And we look at XIoT as basically, I see it as anything connected to a computer network that doesn't have a computer keyboard. So all these devices down here below, and really can't run an agent. And really, the reason I started this company was I wanted to solve the problem that embedded devices weren't getting patched. And how do you solve the problem of delivering a patch without an agent? And got out there and then figured out actually over half these things never have the password changed. So we gotta do that too. And so we did that, and then we ended with discovery. So we've got this this platform to manage these things, and it's all we think about and all we work on. And so these devices, we see just massive propagation of them. They're everywhere, and they're mixed into OT, IT networks, and it's an interesting space. So this term IoT, I actually remember where I was standing the first time I heard it. It was actually at my first startup Endgame, literally in the lobby from one of my board members. I think it was like 2010. He said, "What are you doing about the Internet of Things?" I said, "Man, I don't know, but I'm gonna have to go figure that out." And so that term started being used, I guess, around 2010. Really, I think I remember the internet connected Coke machine at Carnegie Mellon. I think that, or coffee pot, like those were some of the first ones. But when we incorporated this place, Cisco said there were 20 billion IoTs on the internet. Now they say they're about 65 or so. So it is like just a massive explosion. We see this tracking towards 100 billion, and compare that to the number of PCs in the world. There are only 5 billion PCs in the world. That number's pretty flat. So a lot of these little gadgets out there that need to be secured and managed. And obviously the topic today is factories and industrial controls, and most factories and industrial controls are completely controlled by these today. And we've got a fair amount of experience in there.
Yeah, Chris. So before this, I was the CISO at like a hedge fund. And I was like, I don't think I have this problem, or that we even have these devices. And then we started to actually look for them, and we're using Phosphorus, and we're like, oh, there are thousands. And I think the last reading I heard was something like 13,000, when we've only got like 4,000 PCs. So it just a crazy number.
Yeah, that's like, so about 3 to 1 to the computer. So that's like kind of, I think, the middle of the road. I think the least I've seen is 2 per employee, and the most I've seen is 12 to 15 in oil and gas, and different different rates in different sectors. But there definitely more of them, a lot more of them than there are PCs.
Yeah.
So right when we did our Series A financing in 2022, our board chairman, Art Coviello, who is the CEO of RSA and created the RSA conference, said, "Hey, Chris, I need you to give a big picture presentation to our LPs, and don't be technical." I'm like, "Oh, great. Okay." And so I woke up like the day before because I hadn't created anything, and I was trying to think of a comp for this IoT world, and so the first thing I thought of is like, I wonder how many servers are actually in the cloud. And I was going to ask my co-founder, and I thought he'd actually think I was crazy for asking him, so I figured I'd find it myself. So I looked up Amazon's 8K. Amazon's 8K at the time, they said they had 6 million servers. They were roughly 60% of the cloud. So it extrapolates out, it's about 10, 12 million actual servers in the cloud, which compared to the rest of these numbers, not that big. 6 billion desktops, I think it's at 5 to 4, 5 to 6, and 60 to 70 billion IoTs on the way to 100. Now, in terms, we use a Darwinian model of genus and species to break up IoT and OT based on what type of system on chip and firmware they use. And so I divided this into animals. So there are 10 million horses in the world, I guess 8 billion people in the world, and there are actually 60 billion birds in the world. So horses, people, and birds are how you would map animals species onto the Internet of Things. So what we've seen out there, we've sampled, I think, over 3 billion IPs in enterprise networks. The day I founded the company, actually, I founded the company the same day. The reason I founded the company, I was reading this white paper. It was a study on IoT malware, and the study, as a result of studying IoT malware, also discovered the patch rate of IoT. And actually, the reason I started this company was because one sentence. It says the hypothetical half-life of Internet of Things firmware updates is 7 years. I was like, okay, we're building updates. We're building Tanium for IoT, and that number was about right, 3 billion in. And but some other stats surprised me. When we got to about our first million devices, the default password rate on them was about 50%. As we've gotten higher, we see up to 70% of devices have not had a password rotated. When I talk, I don't even count CVSS under 9, but half of them have half of them have an 8. So 80% of them have a 7 or 8, and then but more importantly, 20% have remote code execution. So if you have three devices per employee and 20% have RCE, you've got 0.6 RCEs per person. That's not good. And then one surprised me was end of life. Like, there's an immense amount of end of life out there, 26%, maybe on the way to 30%. But a lot of these devices are end of life, and it's really fundamentally, all this tells a story that these devices, whether they're OT or IoT, a lot of times get plugged in, and once they're plugged in and working, they're not touched, and there is some maintenance that's required to keep them secure.
I think that's a great point, because I think that's kind of emblematic of what I found with the whole kind of PLC world, which is they have a technician that comes in, or industrial engineers or electrical engineers, and they set these things up, and then they never come back unless something breaks. So the people that have to run these things don't necessarily know how to do that. They're just hoping that like nothing changes.
And it makes their life complicated if it's got a password.
Yeah. So a lot of these don't have passwords, which makes my life much easier.
Your life today, your blackout
yeah.
life today.
Yeah, going on the offense side, yeah.
So we're about to pivot into Terrill doing some hacking here, but just I'll tell you some of the devices we see. Cameras there's so many cameras out there; they're everywhere. I see these things as embedded Linux boxes. The average access camera we see, which is one of the most popular, cameras we see in the United States, has 63 critical vulnerabilities out of the box, and not many people patch default credentials, running services on RTSP, OnVid, HTTP, custom APIs. The printers are everywhere. They are old. My co-founder describes them best as F-150s. You just keep putting toner in them and they will run forever. And a lot of these are end of life, but they work fine and people want to accept the risk. But I think one of the biggest exploitabilities I've seen in the last couple of years on the printers is the large format printers where they're scanning documents to the cloud. So we're pulling Azure creds and other creds off the printer because it's basically a scanner to the cloud. And so it's a great pivot. And we have seen some malware pivoting out of printers too to egress data. The ruggedized ones, Zebra is a great company. They're everywhere. they're very critical. At the end of the supply lane or factory chain, that thing doesn't. If that label doesn't print, the box doesn't ship. If that label doesn't print, the prescription can't come out. That bracelet doesn't print out. You can't check into the hospital. So these printers are in some cases really life critical. We see a lot of Modbus gateways. We see a lot of Chinese Modbus gateways. And these are gateways that connect kind of internet protocol to non-IP connected devices. Most UPSs today are connected, and UPSs are very critical. You pop the UPS and turn it off, everything's coming off. And boy, if you pop the UPS and change the password and lock somebody out, you could really do some damage that way. Power distribution units are also very common. We're going to be talking about PLCs today. I like the HVAC controllers a lot. I've been it's a good way to actually count how big a company is to look at the number of HVAC controllers, because it's basically a fixed number per locations. And we also, I think also these, Terrill, fall into the bucket of, oh, please don't change the password because I don't want to forget it when I come back from maintenance.
Yeah, and I mean, people give off a lot of heat, and that's you got to cool them down, or you can't get into the office.
Yeah, I mean, medical infusion pumps are one of the most common devices next to a hospital bed, that and nurse call stations, and they're very critical. They're pumping medications into people, and there are little computers inside. My short assessment of the infusion pumps, and I've taken a couple apart, is they look like my cable modem from 1999, and that's not a good thing. It's very very old firmware, and it needs to be managed, and X control systems, door controllers, always exciting too. I've usually found one with a password of Tyco. Almost everywhere has one door controller with a password of Tyco, which is it's the oxymoron, right? Because it's the door.
Right.
The robots, we're seeing all advanced manufacturing. We're seeing robots everywhere. Fanuc robots, other vendors' robots. I think these should have access control on them as well. Firmware as you get into some of these things is definitely a little trickier for third party to manage. But any of these high valued assets, I look at these and say, okay, are these more important to you than a PC? If they are, then you should probably secure them. And environmental sensors, occupancy sensor came after COVID. Some of the inspiration for this was around the water hack, wasn't it, John?
Yeah, so some of this is around the water hack. I'll talk about one from January when I get through some more slides. But yeah, these problems just keep coming up. I mean, we're seeing more and more malware. We're seeing more and more attacks, and it's really going after critical infrastructure.
Volt Typhoon was a recent one, and I'll tell you, I think I'm even desensitized to these. It was, I think it's 254,000 bots, and we just see such large numbers of IoT out there in clients. I'm like, 250,000, it's not that big a deal. I got customers way more than 250,000, but
Yeah,
then
but
I
going
looked
after
at
that many Soho routers, yeah.
it's a lot, but then I compared it to NotPetya, John, and NotPetya was like only 30,000, and that like shut the world down. And, it was really bad, and so I started to realize actually 250,000 is a lot.
Yeah.
And it's a lot of devices. And then this Frosty Goop, this was these guys turned the heat off, and these weren't houses, these were apartment buildings with thousands of people in them, and they put them down to sub-zero. And that, I think, caught a lot of people's attention. And then we've got,
I mean, it's just mean.
It is like it's probably not going to go away now. Like it's
No.
now it's a thing.
Well,
I'm not going to talk about the last one.
The like Bolt Typhoon stuff I thought was kind of interesting in that, like, the Chinese attackers were essentially using US Soho routers as almost like a money laundering mixing stage, where it didn't stop them from attacking, it just gave them a bunch of valid US IPs to be able to attack stuff from.
Yeah, and well, I mean, the thing is, it's slightly frustrating as practitioners. Most of these are default password issues. I mean, the water company in Pennsylvania, the password was 1111. I mean, like, wow. Like, this is, what
Yeah.
year is it?
Hmm.
And so, I think I went through some of these in an earlier slide, but these are basically what they look like and what we just talked through, and um, uh, it's what we deal with every day, and I think you're going to pick it up now, John.
Sure. I think we got one more, and
Okay, yeah. I mean, there's just some examples. I think you guys know about a lot of this, but these are some examples of, disruption possibilities. We're doing some work in the desalination space. We do some work in the oil and gas space. They're obviously extremely critical, and these environments can be easily disrupted if of a bad actor, especially, one term I don't hear often. Actually, I'm the only person I've heard say this. Maybe I'm not hanging on the right places, but OT insider threat. What is the industrial insider threat? Because none of these have passwords on them. Like, the insider threat, if a bad actor gets inside, it is a soft, chewy center, as we used to say.
it's fascinating. The more and more that I've gotten exposure to this, just how easy this stuff is. Okay, so we're talking PLCs. So these are programmable logic controllers. I think we had done a Phosphorus live that started to touch on this, but these are essentially a real-time operating system. A lot of that comes from the firmware. They are critical and they control all sorts of stuff. A lot of times they'll also then report up to a SCADA or like an HMI. So these can be written in all sorts of things. Sometimes it's C++, Python, but most of the time it's something called ladder logic, and I'll show you guys that. But essentially the way that these things work, and I mean, I can talk through different like some protocols and exploits and stuff like that, but I think to start with, what I really want to focus on is just some basic things about them. So there's a Schneider Electric PLC that's up here in the top right. So the thing to note is those little holes that are on the bottom of it. Sometimes for a PLC, those holes are in the front. So these are for the different input and output modules. So these are exactly what they're calling them. These are input and output ports. They're either digital or they're going to be analog that just control the expression of like voltage. And Chris, feel free to stop me as I'm going through here, because like I've been pretty close to this stuff for the last couple of weeks, so I might I might skip something.
All right, I will.
Okay, so what we wanted to do here was use a simulator, because showing people code doesn't really give you the context of what's going on. So there's a company called Nurtec. They built this really neat thing on top of Unity that allows you to build a digital twin of any device that you've got inside of a manufacturing facility. So they've got a bunch of example ones, demos. We went through and took a look at like their digital factories. So you can see you've got these the robots with giant industrial like 3D printers. When this stuff runs, all of this stuff is active and it's talking to a virtual PLC. So you can actually wire this up to a physical one to be able to see what's going on and test out code with it. So when you zoom in here, you can take a look at specific like a specific device, and here you can see there's some different pieces. There's a button, but the thing to note here, and I'm not sure for those of you that are watching if this is clear, but it says here on the left that you get the digital outputs, and on the right it's digital inputs. Those correspond to those actual holes in the front or bottom of those PLC modules. So when you plug stuff into that, that's a button or a light or something that's either looking for voltage or sending voltage in. So the PLC kind of functions as, a program that is interpreting the inputs and outputs there. So if we take a look at what one of those programs actually looks like, this is where, at least in this particular one, we define the different variables for that program. And the call out here to point out is the center column here is for the address, and you'll see like O.0.5, O.0.3, or I.0.0. Those are the input and output physical ports. So that's what those wires that are wired into the PLC are actually going to map to. And that gives you the variable name that you can use within your piece of software. So as you start to write stuff, you can actually reference those. And it's this idea of creating context, a contact or a coil, where you're essentially waiting for an input, and then you're expressing that voltage and setting it some kind of a value. So this is just a brief example of what structured text looks like. This is going to look more like JavaScript or Python. It's really quite simple. But the thing that's a little bit different about the PLCs, when you start up, you've got the ability to set a bunch of values like you see here. But once that runs, you're effectively inside of a loop. And sometimes this is referred to as like your scan rate, where it's just looping through and constantly going through these different conditionals. So it's saying that for each time that it scans through, if you see this input, or you see this output, or you see some kind of value set, go do these other things. So in this case, we're going to take a look at an industrial mixer. And I promise there's more moving parts to this thing, like some of these are slides, some of it's video. So for this, you've got a tank up top. It's got a valve to open. It's going to put liquid into this big vat. Inside that vat, it's got a turning propeller. It's going to fill up to the water line, and then it's going to drain it out. And here you've got a control center with the red, green, and yellow buttons. Those are actually functional, and we're going to map them into a program. So this is what's called ladder logic. So this is one of the example programs that runs that industrial mixer on a regular basis. So essentially, this is going to, that scan rate is going to go through and read each one of these. And you can think about these as like functions. Within this world, they're referred to as networks. But the easiest way to think about them is like it's a function, it's inside of a loop, and it's just creating conditionals that here, if that start button gets clicked, then you're going to push current across and do these other things. So this is going to look more like an electrical wiring kind of diagram. And those conditionals are called contacts, where the things on the right, where you're setting values and taking action, are called coils. And where I say it's kind of like an electrical like diagram, the two sides of that, you can almost think of as two wires. When those get pushed together, you're closing a circuit, and the power is actually going to flow through. So this is a really simple like program. We've still got the same concept of like variables here. So you've got this valve up, valve down, you've got different flags, but these map to those physical addresses. So when that valve up or down, that's the physical wire that's going to that sensor. So for doing this, you've got to go in and compile these things, and then you transfer them to the PLC. You can push and pull from a PLC in what I call is kind of like self-describing software. The more complex versions of these things actually tell you what the devices are that they're wired up to, the available memory, what the power is going to be, what the processors are. Like, it describes all of that stuff and tells you how the machine is supposed to work. So you can always pull what that piece of software is, but you can also push to it. And what I thought was kind of confusing is the idea of putting software onto the PLC is what they refer to as downloading. Whereas in traditional kind of IT parlance, we think of that as uploading. And I was like, why is that? And I think it has the way that the diagrams are drawn. So when we think from an IT world, the cloud is above us, right? We upload to the public internet. We download from it. When you've got a diagram for like a PLC, The PLCs are beneath your programming station. So we are downloading the program to the PLC versus uploading the existing. I'm seeing Charles Reese is raising his hand. Dan, can you help us out here?
Charles, you are on the program.
So why is this logic not available with Boolean algebra to be able to allow certain ports to open and other ports to close, and understand the fact that if two ports just happen to be censored open, that this thing is in a fail state and shuts down?
Oh, it absolutely can. It's got a bunch more of these networks in here. This is just what I could fit on the screen.
Oh, okay.
Yeah. So the intention here, I think there's like 7 or 8 different networks that are baked into this thing, where it says if this is open, then don't do this, or like it's the default program here is intended to run properly. The next thing that we're going to jump into is how to start to sabotage it.
Yeah, that was one of my points in that respect, and that was the ability to understand that if something changes its level, like to sabotage it, that would automatically shut down.
Right. So it's supposed to. So let me go to this next slide. And so this is the program that's being pushed onto it. What we're showing here is essentially you can see that the push button is lit up. See if we can get this to run. All right, so this is how it's supposed to run. And we've pushed the green button. It's going to start to fill up. It gets to the sensor on the left of that tank, and it's going to light up there and say, "Oh yeah, we triggered this thing, and now it's going to start to drain it." So that's the proper way that it's supposed to function. So if we go back into this program, we can take it and we can decide to edit it. So I essentially deleted all of the other networks that were the additional functions. It's still got the same mapping here, but we're just going to have a single contact that says, if you push this button, then you should start to drain water directly into the tank. So we do that. And this works about as you would expect, except for it's not going to really sabotage it because you've got to hold down that button. Because again, for that contact to connect, it's not a thing that you just like hit it and it keeps going. So we go back to the drawing board a bit because again, I had not written a PLC program until this point, and we do a small change here where we just set a basic variable, and then we say if you're either pushing in the button or the variable is set, then set the variable, then also just keep pouring in. So the idea being that an operator would hit the green button and then all of a sudden it just wouldn't stop. So that's roughly what's supposed to happen here if this video plays properly. So we hit the green button, it starts draining in, it goes up, and then it hits that sensor. The sensor doesn't trigger because there's no logic for it, and it proceeds to then flow over. So if you're the operator here and you go over and you hit the red button like we're doing here, sure, it tried to stop it, but there's no programming within the PLC to do it. So the only way to stop it at that point is either some kind of a manual valve, or you would have to go in and like turn off power. So this is a contrived example, but it's not that contrived because in January, the Iranians were able to break in, and through a human machine interface, were essentially able to do exactly that. So they were able to get into Muleshoe, which is a small town in Texas. And, you know, this is a real thing. They started to overflow a water tank, which it is even easier because they did the HMI, which is kind of the video game of like PLCs, because it gives you a GUI where you can just start to click on buttons. All right, so let's talk HMIs because I think those are becoming more and more popular. We're starting to, I think there was a report from Census out today that talked about that there's a bunch of HMIs that are on the public internet. Now, a bunch of them have been out there for years, so that's not necessarily a groundbreaking thing, but it's not that surprising that they're getting messed with. Okay, so for this one, instead of using a traditional like a factory simulator, I wanted to try to get closer to what's really out there. So with this one, we went in and used Siemens. They're what was called PCS 7. It's now been branded as the Totally Integrated Automation Portal, or TIA. So they were nice enough to have created a number of different example projects, ones that took way longer than they should to get running. But these are working with actual Siemens gear and a Siemens version of a virtual PLC. So we can pull up a project here. You can see it looks similar to the IDE that we had before. The distinction being that we've got two different distinct programs. There's one here that says PLC_2. That's the actual PLC program. And then the thing beneath it is the Cymatic PC station. So that's a rebrand of what used to be called WinCC. It technically still is, but that's where you build this GUI. So if we go in here and we try and take a look at the PLC program, again, the screen's kind of small here, so it cropped it. But essentially, this has all got ladder logic too. So you could define all the variables, all of the mappings. The only real distinction here is that where the logic before was a lot simpler, this stuff has a much more extensive library. And this falls into what's referred to as distributed control systems. So instead of just having an input-output or these contacts and coils, these things can have a dozen inputs, a dozen outputs, lots of conditional things built into each block. And they can also be written with additional languages. I think there's 4 or 5 different styles that are applicable for the standard. So this is just another example of a thing that has additional inputs, and there are massive libraries. So we're not going to get too much into the programming because I've already showed it's pretty easy to modify these things, especially with existing programs. You go and start to tamper with them. So with this, we pull up, we've got our Siemens virtual PLC. In this, we're seeing that it's actually making changes. You've got a chiller, you've got an office that's consuming power. You've got a production facility here. So the idea is that this is load management for a campus. So we can go in and start to see this. And I kind of took the approach of, what is an attacker actually doing when they're looking for this stuff? And as you get in here, you start to see that, there's some stuff that gives you valuable data, but it doesn't mean that you can actually do anything. But with just the de facto from Siemens, oh, it's an automatic mode, or I can switch to manual. And from there, I can go into the energy production side, and all of a sudden they give me this ability to change what the distribution is going to be. So you slide it one way, and all of a sudden your factory goes out. You slide it another way, and all of a sudden the HVAC goes out. And these are real programs that are out there, and they're just that easy. So even if people aren't modifying and pushing a sabotage program, you can still start to screw with it. But imagine you could also push a sabotage program, and all of a sudden a basic change could trigger an irreversible change. So same idea, they've got a water management version. So again, these are basic programs. This one was a little bit different, as it was able to specify what the protocol and what the device that you were going to push to. So this one, again, we pull up the virtual PLC. So this is for a water treatment plant and for wastewater. So once this kicks on, we start getting alerts, a bunch of things that we can start to drill into. This, again, I was coming at this from, I'm an attacker stumbling into this, and what could you start to do with these things? And as you go through it, you find that it's got a lot of different like functionality, most of which you can't use though, because it's got a little bit of security that's baked in. Turns out that it also has a default password. So now as the administrator, you can start going through here and making adjustments. You'll start seeing that like the load goes up, the rain overflow basins start getting full. Here we've got different motors. Let's try changing them, right? You can start to turn on motors and pumps. Same thing over here. We're starting to hit the red line on things. Well, we've got a valve. It's right now locked open. I wonder what happens if we close it. And this is just from starting to click around inside of these things. And, you can turn on additional pumps, to turn off and on additional valves. This starts to break that system down. And just for good measure, it turns out that the ability to authenticate as the administrator, the default password was convenient, but you can go into this program and install a backdoor. The interesting thing I thought was that that authentication is not actually in the PLC though, it's in the HMI. So this is, in kind of web parlance, this would be client-side authentication, because the PLC doesn't care who's sending commands to it. So they're kind of distinct things where the PLC is just trusting that it's going to talk to this thing, and if it's authenticated within the UI, it's still going to trust it. So in theory, you could just point additional commands at the PLC and do the exact same thing. So the last one, Charles. Dan, can you help us out?
Okay. Yeah, the question is what prevents this from becoming a fire sale? Because I mean, these particular SCADA environments are designed to be managed, but the problem is if they're whether they have a default password or not, the average threat actor is going to go out there, just find out if they've got access to it to make these changes, and then keep that in 0 day and wait for the time to roll over and activate all these hacks.
So that's a great question. And when you say fire sale, I'm guessing you're talking about the term from the like Die Hard movie. Yeah. So I don't know if this is the run up to kind of like a cyber Pearl Harbor statement that folks have made, but this is the concern when we're talking about nation states going after industrial control systems.
I agree.
Yeah, I mean it's that you can sit there for a while. This stuff doesn't change. It's not like an immutable thing. But yeah, I mean you could start building up a huge library and a backlog of this stuff. And then all of a sudden you flip the switch, you start pushing out, some bad programs that don't work properly. Like this is what we're talking about when we talk about cyber physical, right? That we're crossing this divide of what are these kind of dumb computers that I think we assume are hackable, gets into the physical side where it's a valve, it's a pump, it's a motor, it's a servo, it's an arm, it's all these things that have an actual physical presence for us.
And I believe this is pretty much what your software does, is go out there and manipulate the data and figure this out.
Yeah, so a lot of what our software does, and this is not intended to be a product pitch, is to go out there and interrogate the devices to be able to leverage these things that they're intended to do, right? I'm not quote unquote hacking these as much as I'm using the devices the way that they were intended, but they were never intended to have this much access or kind of be a thing that people knew about. A lot of this was driven by security through obscurity for the longest time, where most people just didn't know how this stuff worked. I mean, until a month ago, I didn't really understand it. And I was like, I think it works this way, but I wanted to see how to actually do it.
Yeah, for the last several years, I'm going to say plus 7 years, I've been working with SCADA systems and ICS, and all I've seen every day, all day long, is the ability to be able to just walk in there without even a password in most places, if not hacking the simplest. And
Yeah.
then, let's just say, for instance, I've got HVAC access at a colo, and I decide to turn the heat up on everything that's out there and cause everything to fail over a long period of time. That's a wholly
100%.
different. That's a wholly different environment than well, we'll just make that server fail. No, we'll
Yeah,
make the whole plant fail.
and it
Make
talks
all the
back
servers
on,
fail. Yeah.
yeah, it
Yeah,
talks about
Charles.
these things that just don't have these security provisions that were ever conceived.
Yeah, that's a great point, Charles. Like kind of my joke of how do you kill AI? You shut off the air conditioning,
Yeah,
and
exactly.
that's probably the best way.
And the real truth of that matter is that the fact that it can be done, it's a matter of who's monitoring that and at what level. And as I understand it, that's what you're all about.
Yeah,
Yeah,
I'll tell you that they're two major HVAC systems I see, Johnson Controls and Distech, and we understand them very well, and they're important. They're not many of them, but they're important.
yeah.
You understand. All right, let me stop from interrupting you.
No, please. All right. So the last thing I was going to show in here is a bottling plant. This is not, a sophisticated thing. We start this up, we push the software to it. Once our virtual PLC starts running, tanks start filling up, things start moving on a conveyor belt. Again, not particularly interesting, but the HMIs, from a hacker's perspective, you're going to be looking for what actually can you do to change things. So you could put in additional orders, assuming a human's going to be involved there. I can start to understand where my other PLCs are, what they might be connected to. I can't really do much with that. I can see what's going on here, packers, fillers. Like I might be able to fill a tank. I'm not sure if that's something that can cause a problem. But over here, I've got a power button. I can just turn off the production line. That's exactly what you can do. And like, again, there's no passwords with this, there's no security. And these are all things that are intended to work this way. And if you had gone in and modified that such that when they hit the power button, it never comes back, that would be a really simple program. I didn't have to get complicated where like I start putting caps on the wrong size bottles or, all sorts of other things that could disrupt it, but you just turn it off. So that's kind of the run through, just kind of giving people a primer on how you actually load programs on these things, what those programs look like, and what the kind of video gamification of these things starts to look like, where it's just so much easier than like even I had thought it was. So I think part of this also is what I think is an evolving side of like where Stuxnet aside, we've gone from not that sophisticated OT malware to more and more sophisticated malware that's gaining more and more support for more and more devices and more protocols. And I think where we might be headed is that, the next generation of OT and ICS malware might talk all of it. It might talk all of those protocols for all of those devices. And they're really just going to start focus on what types of devices do they want to disrupt? What types of targets do they really want to focus on? Like, I think we could start seeing the ubiquitousness of this kind of next generation of OT malware that's going to make it look a lot more like traditional IT malware. And I think that could really have a huge shift for us. I'm not sure, Chris, do we want to talk about like some of these specific ones like Triton or like Indestroy or like some of those? I'm not sure if Chris is on mute. Hey Dan, I think Charles is raising his hand again.
Yeah, looks
As
like
I've been in this industry for a long time, I think that these are softer targets. I think as the PCs eventually become harder targets, devices with no passwords that haven't been patched in almost a decade are going to become more attractive.
Yeah. And I think
I thought
Charles. Oh, Charles.
is this about? Are we about at the end?
Yeah, yeah.
Dan, if you could make me big, I wouldn't mind. I was going to walk through our office here real quick and show some things.
Yeah, let me stop sharing and
there you go.
Yeah, so I'm here in Nashville, our headquarters. I'm gonna walk backward, but this is my favorite place. This guy has a great job behind me. Eric. Anyway, he's our lab manager. So anyway, part of what we decided to do, this like 7 years ago was in my basement, but to really figure out how to secure all this stuff was basically we had to buy it all. We had to buy one of everything, everything. And if you've been doing this for a little while, the yellow thing behind me is very important, not the robot, the fire extinguisher. And there's something else important in here, which is a big box of paper clips, which can basically reset the password on just about anything. But I just want to show you how we think about these things. You know, we broke up this world of IoT and OT into like a Darwinian model of the genus and species. And what we found is that if you look at devices based on what chip is inside them, when they're made, and what system on chip really, and what firmware they are, you can break them up into reasonably manageable groups. And while they're, these are all different machines, it is surprisingly common that the number of families of firmware are more than tens of thousands, even though the number of variant devices are in the millions.
yeah, Chris, I think the lab's always like it's definitely one of my favorite things to check out when I come down to the office.
Yeah, it's always growing, and it's just great to have a resource where we can put our hands on any of these devices. We see in our environments, and we're literally adding. I'm looking at 20 new machines sitting here about to be racked up, and it's definitely like if for anyone with a short attention span, this is an interesting part of the industry. Um, and yeah, Terrill and I aren't big in, we don't push product when we talk about kind of subject matter areas, but fundamentally why we're here, why we built this was because we want to talk to these devices, not listen, talk to them over the network. So we implemented communications libraries to speak to all these things behind me and then do things like patch them, like change the passwords, like turn off telnet, and everything in between. And so that's what we're doing here. We're building. We've got some great customers that are, making great progress with this. And it does, going back to the original stats I threw out at you guys, 50% CVE, 20% RCE, 70% default creds. Like there are a lot of vulnerabilities here, but it's also, what we decided to do is just make it easy to solve and just grab the biggest buckets of devices and secure them. And it's what we do every day. And it's I've been doing this my whole life, and it's definitely the most interesting job I have. So we'd love to talk to you more about it if you're interested in hearing about it. I think do we have like one
Yeah,
building side with emails on there?
I think we got. Oh yes, so let me put that up, and then I will also.
I guess we have enough
do
time
this
for
in
some
that.
Q&A too. If there's any
Yeah,
more hand raising.
so we've got one question, I think. So the question so far is, just trying to get context. The conversation is post-compromise, right? How easy is it to break ICS if someone gets past the firewall, or if there's no firewall? And so to answer that, like these PLCs, for getting into them, a lot of them don't have passwords. And if you've got network connectivity and you know how to talk that protocol, which the programming environments do, like that's the whole ball game. Like that is the compromise. Like there's no exploit to get on there. There's no, oh, we had to go after the firmware. There are exploits for that stuff. This was, you don't need an exploit because you're doing everything it was intended to do. Like these PLCs are inherently programmable. So if you've got connectivity in most cases, like you can start to get into them. There are certain PLCs that have physical keys to set the mode on them. So sometimes that can prevent you from pushing a modified program, but it doesn't prevent you from pulling what's on there. So again, like it's expecting a lot of this communication back and forth. So there's like, I'm not sure that this is post-compromise as much as this is part of the compromise. Not sure if we've got any more questions. Dan?
Yeah, I'm going to send one over to you.
I've exercised out-of-band management rather than air gapping in many environments. Yeah, the out-of-band management is nice. A lot of folks are trying to focus on like segmentation, but I think ultimately we're finding that these devices are making their way onto common networks that eventually have internet connectivity. And even air gap networks, while they're in a better spot, are not completely like immune to different malware that can cross that. And
there are a lot of vulnerabilities in out-of-band. There's a lot of vulnerabilities in out-of-band management. Terrill, how often do people change the password on their iDirects and ILOs?
Never. And in fact, the next series that we
those
have
things
is
are little
going
embedded computers themselves. So the out-of-band.
Yeah. I mean the Supermicro ones, the Dell ones, the HP ones, like those things are all, you know, a very problematic series of devices.
Well, all right. Well, thanks, John. That was great. Thanks for walking us through those hacks, and thanks for attending and staying on. And you know, we love your feedback and hope to hear from you.
Yeah, thanks everybody.